Hello, everyone. My name is Yuyun Duan. I am a PhD student from Temple University. Today, I'm going to present our paper titled Joint Optimization of Deep Neural Network Partition and Scheduling for Mobile Cloud Computing. In this work, we focus on the DNN inference on mobile devices. In those applications, the inference latency really matters. For example, for face recognition or object detection, we hope they have the real-time response. To reduce the inference latency, those applications usually use pre-trained DNN models, and therefore they only need to execute one round of forward propagation to get the inference results. But even though the inference latency could still be high, our experiment on image classification tasks using Raspberry Pi shows that some model may have over 10,000 milliseconds inference time if we want to have a higher accuracy, as shown in this figure. So we still need to reduce the inference latency. And existing researches has proposed the cooperative deep inference. They noticed that we have powerful cloud servers and fast communication channels. Therefore, we can offload some of the computation workload from local mobile devices to cloud servers with a relatively small communication overhead. And in this way, we can still reduce the overall latency. However, those works only consider the inference task only consider a single inference task. However, in reality, we may need to simultaneously process duplicated inference tasks. These cases, for example, in autopilot or in AR/VR. At the same time, the system may gather pictures from different angles, and they use the same DNN model to process those multiple inputs. And those gives us duplicated inference tasks. They have the same model, but different inputs. And for those duplicated inference tasks, merely consider the partition is not sufficient to get the optimal latency. Besides that, we can also consider the pipeline. We can organize the cooperative inference process in a pipeline, and in this way, we can hide the communication time behind the computation, as shown in this figure. And in this way, we can further reduce the overall inference latency. But it also introduced another problem, which is partition and scheduling problem. In this problem, we want to minimize the overall latency for duplicate inference tasks. And we need to consider both partition and scheduling. The partition means which layer should we cut each model. And the scheduling means after partition, what offloading sequence should we choose to achieve the minimal latency. And actually, this problem is very challenging. It comes from two aspects. One is the exponential partition plans. We know that for each DNN model, the possible partition points equals to number of layers. And the partition for different DNN models are individual. So their combination are exponential. Exhaustively search all those cases is time consuming. And the other challenge comes from the partition and scheduling correlation. By the correlation, I mean the best partition for individual DNN model plus the best pipeline scheduling after that doesn't equal to the optimal latency. As shown in this example, for example, the best partition for each individual DNN model is partition after layer 2. And in this way, the latency for each individual model is 7 plus 2 is 9. But it is not the optimal latency for 2 tasks. Actually, the optimal partition and scheduling strategy is one model should be partitioned after layer 1 and the other one be partitioned after layer 2. And after scheduling, they will have the much smaller latency. So in this work, we consider this scheduling problem, and mainly we organize the DNN models into 2 groups. One is chain structure DNNs. A typical example is AlexNet. And in this figure, it shows an example chain structure DNN box shows a DNN layer. And in chain structure DNNs, we don't have fork or join points. And for partition, we only need to consider after which layer should it be partitioned. And its scheduling can be modeled as a shop scheduling problem, which is NP hard. And also, we consider a much more complex but general model, which is about DAG structure DNN scheduling. A typical example is GoogleNet. In those models, the partition plans are even more complex because they have a DAG structure. And after partition, their scheduling problem can be organized as a DAG shop scheduling problem, which is also NP hard. And we first investigate the chain structure problem. And we observation found that the mobile computation time increases with the partition layers, which means if we want to process more layers on local devices, we need to put more time. And one interesting property is that the computation workloads for layers are actually similar. Therefore, the local computation time increase in nearly linear ratio. And the communication time decreases with cut points layers, which means as we processing more layers on mobile devices, their output tensor size decreases. And more interestingly, because of the pooling layer, the tensor size usually reduces by half or exponentially. Admittedly, in some models, they have bottleneck module as shown in the figure. Within this module, the output tensor size increases with the number of layers. But however, we can treat that as an entire virtual block without considering the potential cut points within this model. That is because there is no need to cost more computation efforts to get a larger tensor output for offloading. And also we notice that the cloud computation time can be ignored since it is much smaller compared with the mobile computation time and the communication time cost. Therefore, based on that, we have our assumption, which is the mobile computation time can fit in a linear function, and the communication time fits in a convex function. And we further relax our problem to continuous domains. And in this way, we can use convex optimization theory to get the optimal solution for that relaxed problem. And the theory tells us that the optimal cut points x star for all DNNs are actually the same. It means all duplicated DNN models should be cut at the same layer, where the mobile computation time equals to the communication time. However, those results cannot be directly applied to our original problem. That is because in reality, we cannot partition a DNN at layer, for example, 2.3. It has to be a discrete domain. And to extend that, we propose two types of cuts. One is a communication-heavy cuts, which is left to the X star, and the computation-heavy cuts, which is right to the X star. And we can adjust the ratio between the two types of cuts to fill in the gap from converging from continuous domain to discrete domain. And then we want to discuss the stack structure scheduling. Actually, for those stack structures, we converted to multi-pass stack by duplicated fork and join points. And after that, we treat each pass as a task, and can use the chain structure, partition, and scheduling strategy to deal with each layer. One thing we want to mention is that when actually executing the task, we don't want to consider this duplication. And we can do that by memorize the layer outputs with some hash tables to avoid the duplicated works. And here shows some experiment results. We implemented our prototype on Raspberry Pi and our lab servers and compared it with local-only strategy, cloud-only strategy, and state-of-the-art partition-only strategy, which only consider one DNN layer partition. And we can see in all cases, our joint partition scheduling strategy have the best results. And here comes more experiment results. And we can notice that the overhead of our algorithm is actually much smaller compared with overall latency. Therefore, it is worth to use the scheduling algorithm because it can significantly reduce the overall latency. And here concludes our paper. We consider the joint partition scheduling problem and consider the two types of DNN structures. One is chain structure and another is stack structure. And our experiment results shows that our partition strategy can significantly reduce the overall latency. And that is all of my today's presentation. Thanks you all for your attention. And I'm glad to take any questions. Thank you.